Good morning, everybody, and welcome to our webinar on irrigation, whereby we will be looking at solutions for pump control and protection. Our presenter today is William Cameron, who is our local guru, as well as our product manager for automation and drives. I'm sure you'll have a number of questions for him throughout the course of the webinar. He really does have a wealth of knowledge, so please, I encourage you to tap into it. My name is Karen Zotter. I'm the marketing manager for EM, and I'll be co-hosting the webinar with William. So before we commence the webinar, I just wanted to run through some of the controls with you. So to reduce the chances of failures or freezes during the course of the webinar, you'll notice your video and microphone have been switched off. So if you do have any questions throughout the course of the webinar, please make use of the controls at the little bottom toggle bar. If you want to have a chat, click on the chat button and it will pop through on the through the chat side. If you want to ask a verbal question, please raise your hand. We'll actually be able to physically see it and then we'll unmute you. And then for all presentation related questions, just click on the Q&A function and then we'll be able to physically answer either in writing or William will answer verbally as well. Then you'll also, we'll launch a poll at the end of the session. It will literally take 2 minutes, but it drastically helps us improve our overall experience. So if you wouldn't mind just taking 2 minutes out of your day to complete the poll, we'd really appreciate it. And without further ado, I'm going to hand over to William.
Thank you, Karen, for the introduction. Hello all. Thanks for joining today. As Karen mentioned, I hope we can have an engaging session. You can see the contents of what we have set up for today. So we're going to have a look at our irrigation offer, a basic overview of what we have to offer at the moment. We're going to just have a quick look at some of the theoretical pump laws to explain why an irrigation system is beneficial to the customer. We'll look at the menu navigation and the setup of our proposed solution, as well as some advanced features, multiple set points, accel, decel, etc. Then we'll have a look at the overall switchgear and wiring of the solution, as well as some software revisions, and to end it off with a little bit of fault finding. In today's session, I've planned to do a live demo as well, so we look forward to that in the middle of the session. All right, so just to have an overview of the actual offer, our irrigation solution, we have, as you can see on the left-hand side, the picture, we have a number of components that make up each panel. The one on the
William,
left,
you're breaking up quite badly.
Okay, sorry about that. My LAN is connected, so it's as good as it's going to get. I apologize if the audio is bad. So the solution is made up of two softwares that we have developed, namely the keypad software, which is created in TP Editor, which is the interface into the internal program which we've created in ISP Soft, Delta's PLC development software. So combining the TP Editor and the ISP Soft, we've created a solution that is built purposely for this type of market, irrigation and constant pressure, but also gives the user a more intuitive look at what's actually happening in the system. It also eliminates a lot of setup. A lot of the parameters and configuration happens internally inside the PLC program that we've set up. And we've only left the basics and some extra advanced parameters that we've created for the user to enter and edit. So it's a lot more intuitive. You can use the screen to navigate quite easily without having to depend on a parameter booklet. So we've tried to make this as user-friendly as possible for you and your clients. Just to have a look at the actual offer, So currently we have the irrigation solutions from 1.5 kilowatt all the way through to 132 kilowatt in our orange sheet metal enclosure. There's a different program versions available as well. For today, we're just going to focus on the single pump constant pressure version, which is obviously the most popular. We also have a couple of versions that we will release early next year. That will be the handover duty with 2 pumps, also constant pressure, and also a level control for borehole applications. They will be relaunched early next year. For today, we'll focus on the single pump. We also have a number of set points for the user to choose, be it just a single set point, your master set point, and or an additional 5, 7, 11, or 15 set points on top of that master set point. So that would make a total of 6, 8, 12, or 16 set points available to the user. These are different pressure set points that you could have pre-stored inside of your variable speed drive. There's also a local and or local remote option, where in the local configuration, your set points and your start and your stop of the system is done locally at the panel, at the pump house. And with the remote option, you can flick it over to remote, where we rely on an external digital signal to select a specific set point and to run the system. So this can be tied in quite easily with a radio control system or any other telemetry like that uses a digital output to send the start signal to the drive. And last but not least is the indoor or outdoor option. So for the indoor, it's basically we don't include these rain hoods or the rain hood on the lip of the panel. And obviously for the outdoor option, we include the rain hoods as well as the extra lip on the panel. I would say the indoor option is IP21, where the outdoor is IP54. So before we get into the actual program, I just wanted to highlight the affinity laws and why does this application, why does this implementation of an irrigation system benefit the user in the end. So the pumping laws or affinity laws, there's 2 types. One is a constant impeller diameter and a variable speed, where the other is a constant shaft speed with a variable impeller. The 2 laws are the same, and we'll be focusing on law 1 with a constant impeller and a variable speed, obviously achieved by the variable speed drive. So you'll notice that your flow is proportional to your speed, your pressure is proportional to the square of the speed, and your power to the cube of the speed. So this means a very small reduction in speed. A small reduction in speed can result in quite a large energy saving component. So if you take a look at the pump curve or a theoretical pump curve of that of a throttling valve versus a VFD, you'll notice that the VFD follows the theoretical pump curve much closer than that of a throttling valve. So if you're operating at your highest efficiency point of the pump, it wouldn't make any difference really if it's running through a direct online system or a VFD, if the pump is operating at 50 hertz all day, every day. However, the energy saving area is in the variable speed part of the drive. So if you can just minus a slight bit of rotational speed off the system, instead of choking a valve, the energy saving that you could yield is quite substantial. So again, that's the 0 point or the point of highest efficiency of the pump. And at that point, your typical bypass and drive are met. But anything below that, you will save a fair bit of energy with a variable speed drive system. So we'll have a quick look at the CP2000 as as a standalone product and the features it has to offer. As most of you will know, it's quite a modular design for the CP2000. So easily removable keypad with a very low cost extension cable. A simple network patch cable is used to extend the drive's keypad, and that can clip directly on the front of your panel. Also, control terminals are easily removable and interchangeable. Fans, easy removable and interchangeable as well for maintenance down the years. And also a host of digital inputs and digital outputs on the control circuit. The CP2000 is very resistant against harsh environments. So built-in EMI filter on 30 kilowatt and under, and a built-in DC choke on 37 kilowatt and up. Also, the enhanced PCB coatings ensure that the control circuits can operate in relatively harsh environments quite stably. The drive has a host of built-in protection, over voltage, under voltage, underload, overload, but we also add in external protection in our pump solution. So that's with our CPT Ciprotec surge and lightning protection, which is standard on all irrigation panels. We found in the areas that the irrigation systems are used, the energy and the supply thereof is normally quite unstable. And the extra protection that the surge as external and internal offer will ensure longevity of the system. So let's have a look at the main page overview. Now this is obviously the custom display that we've developed to give the user and the end client an overview of what's happening on the system. So we can see we have top left-hand corner, the actual set point in pressure. Bar is the unit that we've used. The actual set point in pressure. We've got the current running pressure of the system, top right-hand corner. This is what the pressure transmitter would measure. The motor running speed in hertz. The amps that we are drawing. And also some intuitive countdown time is here to indicate a no-load system is busy timing out. So if your pump is under a no-load condition, we have a countdown timer that will give the user a visual indication that, number one, the system is in a no-load condition and how long it is going to take before that no-load condition has been met. There's also indication of sleep on the display. This will come and go as sleep enables and disables, as well as some other fault indications that we've programmed in, specialist fault parameters. We're using obviously the keypad to navigate through the system menu, and we've developed it in such a manner to make it quite easy to operate. Instead of your parameter book, you've got your control buttons, your function buttons that you can use to navigate up and down through the menus. So you'll note as you go from basic to advanced, or advanced to set points, or set points to accel, decel, the selected menu would be, the font would be larger than the one beforehand. I've got a demonstration of a live demo we have in our offices. We've managed to simulate the exact keypad onto an HMI, which we then can display remotely on this webinar. So for instance, if I go into the menu button, the menu function, you can see my keypad, my main menu. And as I scroll down through the menu options, the current selected menu would obviously be highlighted in this manner. We'll revisit this a little bit later as well, the remote display. So let's go have a look at the basic setup of this irrigation system. So the basic setup is exactly that, the absolute basics. It's 3 pages, and obviously each of these should be looked at as a bare minimum when commissioning an irrigation system. So first and foremost is your rated amps of the pump. This can obviously be found on the motor and entered in into the system over here. Also, the no-load amps of the system can be entered in. You can find out the no-load amps by either running the pump without water and then reading the amps that it draws and then putting maybe 10 or 5% higher than that value into the no-load amps. And then no-load delay is obviously the time it would take once you're running underneath those amps for the system to trip out on a no-load error. This is there obviously to protect the pump, not to protect the drive or the motor, but the pump is the one that needs load or needs water to move. Depends on the pump to how sensitive you want the no load to be. I'm not a pump guru, but some pumps are very sensitive, maybe 30 seconds without water and you could do damage. Some other pumps you could run for a couple of minutes perhaps before any issues might arise. Also on the basic menu, 1 out of 3 is the minimum speed. So this is the absolute minimum that you would like the system to operate at. Generally, we would set that at 30 Hertz as a default when we do a pre-commission. So on the right-hand side, you can see a timing diagram of, say, scenario 1 and scenario 2, where scenario 1, if you're only drawing 110% of your rated amps, the drive would take a little bit longer to trip out. Scenario 2, 120% of rated amps, obviously would trip out a little bit sooner using the I²T formula inside the drive. Scenario 3, if a no-load condition is met, you can see the no-load delay once you're underneath the no-load amps point to where the system would shut down. So once you're below no-load amps, the timer will initialize, and after the timer is counted out, it will trip on a no-load display or an under amperage display. The second part of the basic menu is the transducer setup. Obviously, this is important so that the pressure that you measure in the line is displayed correctly. Normally, I would double check this off a mechanical gauge that's typically on the system as well. But if you just enter in the correct parameters, as you would see on the actual transmitter itself, into the pressure range of that the drive would need, the system should be calibrated accordingly. The next part of this page is the feedback detection time. This is quite an important parameter. If for any reason, if the cable gets cut or the transmitter might fail or a wire breaks off or it's loose, the system would see lower than 4 milliamps. And once the drive registers a signal lower than 4 milliamps, it will start its feedback detection timeout. After the signal has been lower than the detection time, the drive would trip out on a feedback loss. This is obviously necessary that if I don't enable this feedback detection time and I leave it at 0, the function is disabled. So long as I have a value higher than 0, the protection is enabled. If I had to cut the cable without the feedback detection time in place, the drive would register 0 bar and obviously ramp up to full speed and do that forever and a day until something fails. So it's important, in my opinion, to include the feedback detection time in your setup. Last on the basic setup menu is overcurrent stall prevention. So these are parameters that protect the drive from going into an overload condition. So if for whatever reason my amps start to rise, maybe an open pipe or a pipe that has little water inside of it needs to be filled up, your amps can rise sharply, then the overcurrent stall prevention can kick in, and either on acceleration, it will stall the output speed from accelerating anymore until the current falls within a specific level set by yourself, and at which point the the speed will increase again, or overcurrent at normal speed or at running speed, where the drive will actually bring the speed down of the pump in order to keep the amps in check. And maybe once there's enough back pressure on the system and the amps are normalized, the drive can then increase its speed again and operate normally. So these are here to protect the drive from a nuisance overload trip that might be caused by external factors. Let's have a look at the advanced setup. In the advanced menu, we have another sub-menu inside of there, made up of Boost Setup, PID, and Miscellaneous. Now we're going to spend a fair bit of time inside what we call the Boost Setup. This is an intelligent sleep procedure that we've written into the drive to basically increase value with just software. So we'll run over this and do a couple of live demos on the features that we've programmed in for the Boost Setup. So before we get there, let's just have a look at a conventional sleep and wake scenario. So sleep and wake is a pressure percentage of your set point. So 110% of 2 bar would be 2.2 bar, for instance. And the wake percentage similarly is a percentage of the set point as well. So if my wake was set to 50% and my set point was 2 bar, I would wake up at 1 bar of pressure. Okay, this is the standard sleep and wake procedure that the drive has in its own parameters. And it is as it is in the manual in Delta's CP2000 datasheet. I'm not going to spend too much time on this because this is not what I want to discuss. We want to discuss the enhanced features that we've added to the system. So this is the behavior when our boost setup is disabled. Now boost is disabled by default. It's up to the user to decide if he would like to enable this advanced feature or not. So we'll go over in the next few slides about when and why someone would want to activate an advanced sleep, or we call it a boost setup. So the second page on the advanced menu is to activate this boost setup, yes or no. Let's move this up a bit. So I've made this timing chart to kind of guide us to when is boost needed. When do we need to have this advanced feature enabled or not? So if your sleep and wake control is from a digital input, in other words, a computer, or every morning you wake up and you turn the system on, and when you don't want to pump anymore, you turn the system off. That is a digital signal. You are physically going to the panel, turning it on and turning it off when you need it or when you don't. This is a basic setup, so boost is not needed. Okay, so sleep and wake is from a digital input. Yes, we can assume it's a basic setup. All right. If your sleep and wake control to turn the pump off and to turn the pump on, if that is expected to happen from a field valve, from you closing a tap and opening a tap, you would like the system to completely shut down and you'd like the system to completely start up again. If that is the case, we should consider enabling the boost option. If the sleep and wake detection is stable, then there's no need to enable boost. So we can say boost disabled and we can keep the setup quite a basic one. However, if the detection of sleep and wake from closing and opening a field valve is not stable or it's unstable, then we should definitely consider to enable boost. Okay. So very often you might close a valve in the field, and depending on a number of factors, pipeline, pipe bends, accumulators in the system, or there's a number of factors to consider, even the type of pump. Very often the system might just stall in a pressure control and not go into sleep. And if this is the case, then we can enable the boost option. So the boost option is there to detect the fact that you're not pumping water anymore. And we have three methods of doing this. Either by looking at the running amps being below a certain level, that we know we're not doing any work anymore and we can begin our shutdown procedure, or the running hertz being below a certain frequency, where we can also start to initiate the automatic shutdown procedure. The third one is a little bit more advanced, which was a request from one of our good clients, and we had included it as an option for them in particular. So we'll focus on the first two options, the boost on low amps or the boost on low frequency. These two are by far the most commonly used by our clients. All right, so if we had selected, for instance, a boost on amps, then we would enter in the low amp point over here. If we had selected boost on frequency, we would select the boost frequency over here. I'll do that quickly on our page. Let's just start over again. So our main page, go into the setup, into our advanced menu, into advanced, into our boost setup. There you can see my percentage of 2 bar as my current set point. Boost detection is enabled. It's a yes, it's a 1. So it is enabled, and I'm asking it to use amps as its detection for that boost procedure. You'll see in the next page that the actual frequency entry would be disabled, and it would only allow us to enter in the amperage that we wanted to detect at. Okay. Once the system starts to detect boost, or starts to recognize an amps are too low, or your speed is too low, and it needs to go into its shutdown procedure or its sleep pattern, it will start a boost delay timer. Okay, so this is the time it will take from being under the amps or under the frequencies before the actual boost is initialized. Now, once the boost is initialized, the user has an acceleration and a deceleration to choose from. So once that boost point happens, you can choose a sharper acceleration and deceleration to perhaps lift the pressure, maybe 5, 10, or 20% above your set point, and then quickly bring the pump to a stop, as to allow the non-return or the check valve to seal properly and to keep the system pressurized. Obviously, if the system can't be kept pressurized, or the check valve is faulty, or there's a tap that's still open, you would lose pressure and the system will fall below the wake pressure again and start up again. That's a type of oscillation that you need to ensure doesn't happen. So make sure your check valve is working properly, make sure there's no leaks in the field, and then the system can hold pressure in the discharge side of the pump. So we've got the delay time before we actually go into our advanced sleep, and our accel and decel once that point is reached. So here's a timing chart of how the system would react to boost selection being on amps. So as the pump increases speed, gets up to a speed where we're at constant pressure, maintaining constant pressure. If we had to lose our, if we had to close our outlet and force the system and shut off a new valve, stop water flow, our amps could drop drastically below our boost amp point, at which time the boost delay timer will kick in. Once that time has elapsed, the system can accelerate at the boost acceleration rate that we've programmed, and it can also attempt to get to a higher sleep pressure, higher than that of our actual set point. So once the pump reaches that sleep point that we programmed in, 110, 120% perhaps, then it would deaccelerate at the boost decel time and only restart once your pressure drops below your wake pressure point. In other words, once a tap is opened again, it would then wake up and continue operating. The option for the frequency when our frequency is lower than a specific point. I found in a number of years that this option is more typical for a smaller pump set. So when you only have a few amps to play with, 2-amp motor or a 3-amp motor, it's very difficult to sense that difference point of load or no load. There might only be 0.1 or 0.2 amps in difference between an actual load scenario or a no load scenario. In that case, we've often found that using the frequency detection method is better. So we use frequency detection when your boost amps or your no load amps is very close to your actual running amp condition. All right. Let's do a quick simulation of that exact setup right now. So this is my HMI that I have, and we're going to quickly do a basic setup for that. So we've selected amps as our sleep. We've got 1.5 amps, should be okay. Boost delay is 20 seconds. Axle is a little bit too short, so, and my boost acceleration is 2 seconds, boost deceleration is 3 seconds. Okay. We'll go to the rest of the parameters just now. So here's my system. If I enable one of my field valves, you'll notice my pressure would drop drastically, and then I'll enable the drive to run in automatic mode. So while I'm below 1.5 amps, I'm detecting boost. But as soon as I go over 1.5 amps, that timer will stop detecting there's no load. So I'm happy that I'm running above load with over my 1.5 amps. This is a small pump, so amps, in my opinion, is not the best to detect on, but we have just enough differential to use it in this scenario. So if I open up another valve, you'll note that my speed goes up, my amps also go up, but my pressure remains the same. And the same if I open up another zone, my speed goes up, my pressure remains the same. Amps also increase slightly. Let's just bring it back down to one valve. All right, so if I disable the last valve, water has nowhere to go. I'm pumping up against a closed valve now. My amps drop to 1.4, which is below my 1.5 mark. And now the system starts to time out. So this gives you a nice visual to note how the dynamics of your system are operating. Once the timer has reached its end point, the system will initiate its boost and try and achieve that 2.1 bar that we set. Once that 2.1 bar or the 2.2 bar is achieved, the system will start to deaccelerate and sleep. So sleep is also indicated over here in our advanced sleep that we have programmed. Again, I open up a valve, pressure will drop immediately, and the system will kick off. This is done on a very, very compact rig. So there's hardly any expansion for the pipes. It's a very, very compact rig. Out of the pump, through a sprinkler set and back down into the pump. So this is one of the worst case scenarios you could have when trying to set up this advanced sleep, or as we call it, boost. I'll do it one more time just to show it's not luck. Turn it off. We count down our 20 seconds. At that boost point, it will reach our sleep pressure and then start to shut itself down. All right. You can see that's the point at which I've slept at. If I wanted to increase that point, I could just go increase my sleep frequency. F2, I think I could get to 120%, which is 2.4 bar. So this allows you to set a bigger differential and perhaps eliminate a continuous start and stop to sleep at a higher pressure and allow the system to leak slowly, for instance. So we'll turn on our system again. Sorry, we're going to wait another 20 seconds. Off. If I happen to go back to 1.5 amps, this timer would reset and would have to start over again. So now the system should attempt to get to 2.4 bar before shutting down. Here we go. And the net result of that is that my actual resting pressure is now higher than what it was before. So theoretically, it would take longer for this 1.95 to leak out into 1 bar. Also for maybe commercial applications, if you're doing it like this, the initial tap that you turn on has a little bit of water coming out because of this pressure in the line, giving the pump time to catch up with the demand. Okay, so that is your sleep on amps. We'll quickly go and set it for sleep on frequency, just so that we can note the difference. So what's next? So our option for boost is enabled, except we wanted to detect boost on frequency, which is number 1. Tells us we're in frequency. And my frequency detection is set to 41 hertz. So anything lower than 41 hertz will enable frequency detection to start timing out. And you can note that my boost on amps is now disabled because I've changed my detection point. Let's go back. All right, so let's go back into automatic mode and open a valve, open a couple. See, I'm below 41 and it's counting out, but as soon as we go above 41, that timeout would stop. So it's important that that timeout is longer than, say, your acceleration rate. Otherwise, you're going to be stuck in a never-ending loop. So we'll turn one off. I'm still above my 41 hertz, maintaining my 2 bars. If I turn another valve off, my pump doesn't need to be, can go lower than 41 to maintain the 2, and to maintain the 2 bar. I'll count out, and now the same procedure would happen, just using a different detection method to detect that no load. There we go. And the net result is much the same. You can see that in the frequency option, we've got from 42.5 hertz all the way to 41.00 hertz. So there's like 150 digital points between load and no load, where in the amps detection, there's only 0.1 of an amp. So this is a small pump, like I said before, so it's probably better off to use the hertz detection than the actual amperage detection. However, that being said, often the amps are the one to be used. Often these pumps are not 0.1 or 1 kilowatt or 2 kilowatt units. They're a lot bigger than that. And that gives us a lot more amps to decide if a differential is happening or not between load and no load. All right, I'm not going to look at the detection method using both. Like I said, that's more of a specialist setup. So we'll just go past that to save a little bit of time. The next option is the dry run error detection. So this is very important. If you have enabled boost, I advise you that we enable this dry run protection as well. So what this helps us with is, if we don't reach the sleep pressure, in other words, if there's no water to pump and to actually hit a higher pressure, the system will never ever go to sleep. However, it will attempt to hit that pressure. So we would give it a dry run time of, say, 10 seconds. And this means it's got 10 seconds to hit that pressure before a dry run would kick out. As you could note in the simulation, it's a matter of 1 or 2 seconds at most. And typically the system will detect that extra pressure if there is water in the pipes. But if there's not, if the inlet is perhaps closed, the load will drop, no load will start counting out, but when the boost point is triggered, there's no pressure to get to that point. There's no pressure to reach your sleep pressure. At which point the dry run timer will start running and trip the system out if it can't get to that sleep pressure. There's also an option for automatically restarting after a dry run error has happened. Perhaps you're pumping out of a borehole or a dam or a river that maybe can run low, and you might want it to attempt an automatic restart after the fact that tripped on dry run. That is achieved in the next page. I'm not going to go through the dry run. We can actually simulate it. The next page is our auto restart timer for the dry run. And this can be anything from 1 second to 24 hours that you can have the restart delay timeout for. So you set your seconds up here, you set how many minutes you want here, and you set how many hours you want here. We can actually do a simulation on that. I could set my sleep pressure to a value that's very high to simulate the lack of getting to a sleep point. Sorry, I'm not by the rig, so I can't actually physically shut the valve out. If I say 200%, I don't think the pump can get to 4 bar. So we'll attempt, well, let's just go make sure our dry run is enabled. I need to get to 4 bar of pressure. Still the same detection method. Boost delay is 20 seconds. Dry run time is 5 seconds. I've got 5 seconds to get to that 4 bar. If the pump can't do that, then it will trip on a dry run. Auto restart is enabled, and that's set to 30 seconds. We can actually change that to F2. Let's just do a 10-second restart. Let's not waste any more of your time. And let's go back. And open a valve. Pressure drops to wake pressure. System runs. There we go. Settle. So once now the valve is closed, I go below my 41 Hertz, the detection point. If it hits 4 bar, well, then I can't prove it like this, but I don't think it will. Yeah, got to 4 bar. So I can't prove that the dry run would work. You'll just have to take my word for it. So if I couldn't get to that 4 bar point, obviously it would attempt that boost for 5 seconds and then trip on dry run. You'll note now that my holding pressure is 3.2 bar, which is fantastic because it gives me a huge differential before the actual wake pressure is reached. All right. So back to the presentation. Also in the advanced menu, we have a PID setup. Perhaps 0.1% of the time it's necessary for the user to adjust these PID settings. I can probably count on one hand the amount of occasions we needed to. It's here for that 0.1% of the time options, but generally you don't need to adjust the default PID values. P gain of 1 and I gain of 1 is very good control that we've seen from the field. So only in extreme cases do you really need to adjust the PID gain values. And then last in the advanced menu, we've got the miscellaneous setup. Here we've got a no flow detection through a digital switch. So if you have a digital paddle or an inline flow switch that you would like to use for no flow detection, you can enable it over here. So any setting that is above 0 will enable this no flow detection. And you'll note that you have to be above a specific speed for the internal circuit to be looked at. And once you're above that no flow hertz and you lose your digital signal, the system enables a no-flow delay before you would trip on a no-flow error. So you have to be at a specific speed where you deem there to be flow. And if there's not flow, you delay for that time and then trip out on a no-flow error. There's also an option to quickly change the pump direction from forward to reverse. And that indication is shown on this little LED over here. So once you select reverse or forward, forward would be a green LED and reverse would turn that LED on the keypad red. You can obviously also swap your UVW phases around to change the direction, but depends on the gauge of the cables, how easy that is going to be or not. So we can swap the direction over here. Also, we've added a runtime display, so you can note of how many days and minutes the system has been running for. Nice for perhaps maintenance purposes. Last on the advanced menu was another request from a client for pipe burst detection. So that's a very simple detection that we've added, where if you are below your pipe burst pressure, in other words, which is typically below your set point, for a trip delay time, the system will think that there's a pipe that has burst, you can't get to your pressure, and it would trip. The pipe burst timer is set in minutes, not seconds, but minutes. So you try not to have this interfere with any other trip delays. Again, this is based off of pressure. So you need to be below a certain pressure for a certain amount of time. If that's the case, pipe burst can be enabled and triggered. All right, onto some set points. So these are pre-stored set points in the drive. You obviously have your master set point, which is on the main page. You can change your system's set point over here, 1.2 bar. That is your master set point, 2 bar. Or you can preload your set points if you've chosen an option with more than just one set point. You go to your set points here. Set points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, all the way up to 15. All right, so the set points are either triggered in local mode via the rotary selector switch. That rotary selector switch is a BCD switch, and it would bring in 15 preset speeds based off of only 4 digital inputs onto the drive. The same set points are triggered in the remote operating mode via the digital input that would come from an irrigation radio controller or something like that. So there are up to 16 set points, including your master. So for a farm that's got perhaps different types of crops needing different water, or perhaps on different contours, it's great to have different preset pressures that the pump can operate at. Last on the setup is the accel and decel. So our acceleration time 1 and decel time 1. So that is fairly basic. Most variable speed drives have it. Your acceleration rate from 0 to full speed is set up in time 1, and your deceleration rate from full speed to 0 is set up here in F3. For borehole pumps, we've noticed that often the manufacturers of the borehole pump expect a certain acceleration rate, particularly from the 0 to say mid-speed zone. Often these submersible pumps need to have a slightly higher starting torque, and I've seen in a number of the manuals that they do advise on quite a sharp initial acceleration, whereafter you can have a more gradual acceleration. So we've programmed this feature in. So if you select acceleration 2 as a yes, then you get acceleration 2 time, which is set up on the next page. So this will be acceleration time 2 and acceleration time 1. Time 1 is generally sharper. and you also get to choose your changeover point, where we would change over from time 1 to time 2. Typically, that's at about the 30 hertz mark. I've seen that in a number of submersible pump manufacturers' data sheets. So this is mainly for submersible pumps. On your typical above ground centrifugal pump, I don't think it's necessary to have this type of acceleration profile, but then you can just choose no for the acceleration time 2. So typically used on submersible pumps where you have a multi-axle. There's also a manual option. So perhaps if your transmitter had failed, or perhaps you haven't installed it yet, but you want to run the pump, you can put them over to a manual mode. At which point, let's turn the pump on. At which point in manual mode, it will run at whatever speed you have set on the potentiometer. Our potentiometer is sitting at the 0 point. So that's why it's controlling at 30 hertz. And the potentiometer range that you're allowed to adjust is from minimum speed that you have set up to maximum speed. So no one can go to your panel and turn it all the way down and the pump can run at 2 hertz, for instance. The adjustment range is linked to the minimum speed parameter that you've entered. We also have an option for manual acceleration if you would like your manual speed to accelerate at a different rate to your automatic control. You can have a manual acceleration. But if you want your manual and your automatic to be identical in terms of the acceleration rates, then you can just select yes, that you want to use auto acceleration in manual mode here. So that's just a simple yes, no option to use your automatic acceleration rates identical as it would be in manual. All right. So let's have a look at the electrical drawings of the system. So our power circuit is made up of a number of components that we stock at Electromechanica, all very reputable brands: Delta, Lovato, CPT, Hager, Wieland. So our power circuit is, we don't use any inferior items. We only use what we believe in and what we sell. The multi-set point selector switch is a Baco BCD switch, also something we sell. And for the remote set point control, they trigger finder relays, which are also very high quality. For your front panel control and your pressure transmitter, we've got Lovato push button selector switches and pilot lights, and Huber pressure transmitters. And last but not least, we have some flow switch options as well. If you want to use the digital flow switch, we do have some flow switch options from Matic. All right, some program explanation. So you'll see on the main page that there is a little block at the bottom which gives us a program explanation to what version of software the panel has. We obviously try and improve our software as far as possible. And if we find an improvement that we can apply, we would then increment the number by 7.1, 7.2, so on, so on, and so on. I think at the moment we are sitting around 8.1 or 8.2, obviously adding features as we get feedback from our clients in the field. There's also the last option, which would be S for single pump, HD if it's a handover duty pump, or a B for a borehole or level control system. So at a quick glance on your main page, you will be able to know your version of software as well as the type of pump control that you have. This is quite important if you're phoning in for some support on your system, that you know what version you have and what version you're running. The TP editor and the ISP soft that we use to program these systems To connect the drive to your computer, you would need a Delta IFD 6530 USB to RS485 converter. So this is the little interface device that allows the PC to talk to the variable speed drive, so we can program these types of interface screens and obviously the types of procedures that we've been discussing. A couple of fault codes, a couple of common fault codes that you might experience during the commissioning or over time. We've obviously got our custom built fault menu, which will pop up to show you dry run error, a no flow error through the digital input, or a pipe burst error. These are obviously programmed errors or programmed features that we've enabled. And these program features will pop up on this fault menu on the keypad. For any other type of drive fault, it would appear on the keypad as you see here. So overcurrent on acceleration, overcurrent deacceleration, normal speed or ground faults. These are the typical errors that you could have. They would pop up on the display. Also, any low voltage error, basically if your isolator is switched off or your breaker is turned off, or obviously if ESCOM is turning off, you can get a whole bunch of low voltage errors. Depends if you're accelerating at the time or you're deaccelerating at the time, or you're running at a normal speed. When the low voltage happened, the drive would trip in a particular error. Also, phase loss is a common one, particularly in the outlying regions where power quality is relatively poor. The drive has built-in phase loss protection, so that if you do lose a phase, the motor doesn't end up burning out itself. The drive will detect that and trip on a phase loss error. Also, some overheat errors. Perhaps if ventilation in the panel has gotten worse, or perhaps a fan has failed or a filter has clogged up, it's possible that the drive could experience an over temperature trip. If that's the case, check all ventilation, check all the fans, yeah, that's probably the best root cause to go and fault find for over temperature errors, fans and ventilation. Also overload, electronic overload, and the one we discussed previously, feedback loss. That's where you lose your pressure transmitter. All right. That's about it for today's irrigation system. We have another webinar from Lovato coming up in mid-December, also around pump controls. But this is from Lovato's perspective and their own design and their own systems. So I hope you guys can join us for that, the 15th of December. It'll be great to see you there. If there's any questions, please, I'm more than happy to answer anything. If not, I hope you all have a splendid day.
Thanks so much, William. Really, really appreciate it. Are there any questions for William while we've got the floor open?
I hope the audio was okay. I'm not sure if it dipped again, Karen.
No, I actually think it was from my side, William. It seemed the feedback I got, it was my side, not yours. Right. So it doesn't seem like there's any questions coming through. What I have done is I've popped your email address up on the chat. So if anybody wants to direct any questions through to you, it is there. It's williamc@em.co.za. But thanks once again, William, for your very informative presentation. As always, it's been spectacular. We will email the recording of the webinar to everybody that registered and participated in the next 48 hours. So keep an eye out on your mail for that, or you can also go through to our EM YouTube channel and you'll be able to access the webinar there. And yeah, I'm going to launch the poll and thank everybody for their time. And yeah, if you've got any queries, please don't hesitate to contact us. But thanks very much. Thanks, William.
Cool. I'll stay online in case there are any questions, so please feel free to ask.
Okay, great.
Otherwise, I'll just play around with this little system here. It's always fun. You can see where sleep was initialized as the pressure spiked, amps dropped off, flow dropped off, and we're holding pressure. So this is another view of the, just another view on the sleep procedure from a graphical interface and a trend.
William, a question has popped through. Can the system be fitted with solar panels?
That's a very, very good question. Yes, the system can be fitted with solar panels. We are going to launch quite soon, say like an add-on enclosure. So if you have an existing irrigation system, you could put an enclosure next door to it and feed in solar power as well as having your constant ESCOM supply. Now, what's very important to remember is that we are controlling on pressure, typically pressure or speed set point. So yes, you can add solar, but you always need to have ESCOM as well. Okay, so how you would add solar onto the irrigation system is through a set of power blocking diodes to ensure that the drives doesn't feed back to the solar panels, but that the solar panels only feed current towards the drive. So yes, panels can be arranged. It's very important that you get the voltages right when you are designing your solar array, so that at that voltage maximum point of your panels, it's quite equivalent to where ESCOM would be. If you want to chat more about it, we can do offline. I did go into more detail on that on the hybrid setup. So, but yes, it is possible to add your solar panels to the irrigation system. And remember that you're controlling on pressure, not on solar radiation.
Okay, great. Thank you. We've got a couple of questions popping through now. Regarding the hybrid system connecting, just looking for more information regarding the hybrid system connecting the PV to the DC bus.
Cool. I'll happy to share that with you. Perhaps offline. Armand. Yes, from Armand, eh?
From Armand.
Okay, I'm happy to share that with you offline. Otherwise, I need to go find my presentation and do that. So Armand, unless there's someone else who wants to see it, I'll be more than happy to share it with you, Armand, afterwards.
Yeah, it looks like it's just Armand that's requested it. Okay, I'll pop you through the email address, William. And then, yeah, can you show a live demo of the solar system?
Okay, so our solar system is also running live. Let's have a look there. I'll just need to close that down. Open up the remote. So our solar system is also running. It's a very nice sunny day in Cape Town. So I'm pretty sure, which one is it, this one? I'm pretty sure she's going to be running quite nicely. Let's upload that screen information. We also have an HMI looking at one of our solar drives. So it's quite nice that we can show you these figures live. Okay, Armand, I see your further chat. I think we need to pick up this conversation, Armand, after the session. So I have your details. If you don't, there we go. I have your email address, Armand. So I'll drop you a line, or you can always call the office and just ask for William, and we can have a direct chat. But I'll definitely get hold of you after the fact. Yes, here we go. So this is our solar system. You can see this is our current running point, almost at 50 hertz, almost flat out. Where we started up this morning was, what time? 7:30 we started, and as been running through the day, our speed has increased. And you can see our VMP tracker working over here as well. So Deval, I hope you like that. This is our solar system. We have a real-time chart. This would sample every 5 or 6 minutes. But we have a real-time chart as well, which is sampling a lot faster. And you can see we are just about at full speed, 50 Hertz. Cool.
Okay,
Cool, Amant.
like
We'll have a chat afterwards, yeah.
Perfect. Thanks, William. Thanks very much. Thanks for the question, Armand. It doesn't look like there's any further questions coming through at this stage, but yeah, I suppose let's just stay online in case there are any other questions that pop up.
I can click around and play, so I'm quite happy. Just on this setup as well, you would note that you know, the value of the HMI they can add to the system, particularly if you want to impress a client. We've included all the parameters for the solar system. So quite easy to adjust if I want to change my acceleration or PID values or anything like that. It can all be adjusted relatively easy off an HMI rather than going to the actual drive's keypad, the little keypad on the drive here and punching in parameters, etc., etc. I don't have much history here, no. All right. Thanks, Deval, for asking for that. I'm sure other people might have enjoyed it. Cool.
Right, it doesn't seem like there's any further questions.
All right, then I'll stop the share and stop the recording. Thanks all for joining, and hopefully see you on the 15th of December. Cheers.
Great.
Happy irrigating.